in this video, we are going to discuss cosets and Lagrange's theorem. So first, let us see the definition. Let G be a group. We take a group and H be a non-empty subset of G. Here H is a non-empty subset. We consider a non-empty subset of G. So first of all, we take a group and then H, another object is taken, that is a subset of G. HB, there is no need that it may not be strictly a subgroup. So you can take any subset. HB a subset of a non-empty subset of G. So no need to take a subgroup. So for any element A belonging to G, for any A in G, the set we can define a new set. We can define that set is AH. How do we get this set? How do we define this set? By multiplying each element of H by A. We multiply each element. We pre-multiply. That's very important. We have to pre-multiply. That means the element must be the element which we use to multiply should be used before that element of the set H. So AH such that H is an element of H is denoted by, and this set is, then we get a new set. That set will be denoted by A capital H, because we are considering in the multiplication, we are considering all elements in H. Therefore you can write A into H, AH, A capital H. And in a similar way we can define H into A, H into your HA, we can define HA, that equal to set H into A. Here you can see that the multiplication is on the right. So you are multiplying A on the right. Every element of H is multiplied by A on the right. So HA such that H is an element of H. And also we can define related to this A inverse can be defined. H into A inverse is equal to A inverse, where H belongs to H. So these are the three sets we define three sets related to H and an element taken from an arbitrarily chosen element from G. Okay. When H is a subgroup of G, but let's think about a special case. When that special case is when H is a subgroup of G. So when H is a subgroup of G, AH is called the left coset. So the definition for this kind of set was given. It is given as a general situation, as a general case. But we can specifically we can consider a specific situation, that is H is a subgroup of G. When H is a subgroup of G, then the set, the newly defined set A into H, AH is called the left coset of H in G, left coset of the subgroup H in G. From the general situation, we are now coming to the particular case when H is a subgroup of G, and that contains then that will contain clearly that will contain, then the new set AH will contain the element A, because you know H is a subgroup of G and H contains the identity element. Since H is a subgroup of G, H contains the identity element E, and when E is there in H, when E is there in H, since we multiply every element of H by A, then A into E will be there. A into E is equal to A. The element A into E equal to A, so A is also an element of the new set AH. Then HA is can also be defined. When H is a subgroup, we can define HA, and it is called the right coset. So what is a left coset? Left coset is formed by using a subgroup of a given group. Here the given group is G, and H is the subgroup. So we have to take a subgroup of the group and an arbitrary element A of G, A of the original group A. A is an element of the group, and then we multiply every element of the subgroup by the element A, and it is written as it is represented by AH. So that is the left coset. In the similar way, we can define the right coset, HA. Next, we are now going to discuss some examples. We can use some familiar groups to study this example. Here the given group. In the first example, see, we are taking the group G equal to S3. The group G equal to S3 is taken, and and what is the subgroup chosen? So G equal to S3, and then it contains how many elements it contains. S3 is the set of all permutations of 3 elements. S3 contains the permutations, all permutations choosing 3 elements, or permutations of 3 elements. So you know that there are 3 factorial equal to 6, 3 factorial equal to 6. So 6 elements are there in S3, and we take H equal to the set 1, and 1 here it is the cyclic. It is the it is the cyclic cyclic permutation. So the cyclic permutation which contains only one element. See, one in single bracket. One in single bracket means the cyclic permutation. It's a cyclic permutation because we are writing that identity element. Actually, it is the identity element. One means the identity element. It is the cyclic permutation. Cyclic permutation which fixes the first element. That means it fixes all the remaining elements. So this is the this is the first element, and then the second element we can expand it. One is mapped to 1, then 2 is, then remaining elements are also fixed. So 1 to 1, then 2 to 1, 3 to 1, 3 to 1. Okay, since we consider only 3 elements, so 1 to 1, 2 to 1, 3 to 1 are the elements in this permutation. Next here, the second element is 1 to 3 here. 1 to 3 and then 3 to 1, 3 to 1, but it fixes the permutation fixes the third element 2 to 2. 2 is then 2 is constant, 2 to 2, 2 is mapped to 2. So these are the 2 elements in the subset it is taken, which is taken here, and then how can we form the cosets? Now you can verify that if it is whether it is a group or not. So you can verify whether it is a group. So if it is a group, then 1 3 must be the inverse of 1 3. If it's a group, 1 3 is the 1 3 must be the inverse of 1 3. Let's check that whether it is true. See here, 1 is mapped to 3 and 3 is mapped to 1. Okay, therefore when we take once again that, so see, since 1 is mapped to 3 and 3 is mapped to 1, so when in the combination or in the in the product, so when we take the what we can say, the product of the permutations, the product of permutation we consider 1 3 2 times. So 1 3 dot 1 3. In 1 3 dot 1 3 you can see that 1 3 will be mapped, 1 will be mapped to 1 and 3 will be mapped to 3. Therefore the inverse of this element is the same element, and hence this is a group. So we can say that it's a subgroup of so H is a subgroup of G equal to S3, and so we can define we can using this subgroup we can find the cosets. So see, you can see that by taking H, the elements of there are only two elements in H, and then all the elements of H are taken here, and it is then multiplied by the elements of by each element of, you have to consider each element of G. How many elements are there in G? It contains in G there are 6 elements. What are those elements? See, first one is the identity element. Identity element is 1. It's the single element cycle. It's 1 element cycle. So 1 dot H, 1 into H equal to H itself. That's clear, right? It's because this is the identity element. Since this element is the identity element in G, so 1 dot H equal to H. And next element we take the next element, that's 1 2, the cyclic permutation 1 2. So it has the arrange in the second row. One has 2 in the second row, 2 has 1 in the second row, and in the third element 3 fixes that element. 3 is fixed. So 3 3. So therefore, in the expansion, in the full in the complete form of this permutation, it is 1 2 2 1 and 3 3. So that element is then used to multiply, pre-multiply h, and then we get that the answer in the answer set is, or the answer is 1 2, because h contains identity. First one is the identity permutation. So identity permutation, when multiplied by any permutation, it gives the same permutation 1 2. Thus we get 1 2 as the first element, and the second element is 1 2 when multiplied by this element 1 3. So 1 2 dot 1 3, 1 2 1 3. Now you can combine it using that expanded form of these the two permutations. Here you have two permutations. You can find the composition of this permutation. You can combine this permutation and you get to that it's a single permutation. You will get the single permutation 1 3 2. So it is a cycle. 1 3 2 is the cycle, such that 1 3 2 in the next row it is 3 2 1. The elements are 3 2 1, 1 3 2 and 3 2 1. Okay, and you can see that this is equal to this answer set. This set can also be written as 1 3 2 into h. So one way we find 1 2 into h, and then we get the simplified form of the set. Elements elements simplified in the set, and we get that it's equal to, you are able to show that it is equal to 1 3 2, the element 1 3 2 into h. Thus here intersection of two cosets take place here. And this is a coset, and this is a coset formed by using 1 2, and this is the coset of h formed by using the element 1 3 2. Again, you can consider 1 3 into h. 1 3 is another element of the group. So 1 3 into h equal to 1 3 into h equal to 1 3. You see, h is again when referring the referring the group subgroup 1 3 1 and 1 3, cycle 1 and 1 3, cycle 1 3. When 1 is identity element, since this is the identity element, so when 1 is multiplied by 1 3, and you get 1 3 there. So 1 3, it is the first element is 1 3, and 1 3 into 1 3. The second element then becomes 1 3 dot 1 3. But 1 3 dot 1 3, we have seen that here. Just a few seconds, a few minutes back, we have seen that 1 3 into 1 3. 1 3 is the inverse of the 1 3. 1 3 has the same element as its inverse. So 1 3 into 1 3 equal to identity element. Therefore, the product is 1 3 comma 1 3. So 1 3 comma 1 in the cyclic group of 1. The cyclic permutation 1, that equal to h itself. So you get h equal to 1 3 into h. And one more is there. One more possibility is there. So you can take 2 3, the element 2 3, which belongs to G, and that can be used to multiply h, and then you can verify that you are going to get 2 3 comma 2 3, because one identity element multiplied by 2 3 gives us 2 3, and the second element multiplication, the second position is 2 3 into 1 3, and that can be simplified to get 1 2 3, and the first element is 2 3. The cyclic permutation 2 3, and this is the cyclic permutation 1 2 3. And also you can see, finally you can see that it can be written as, it can also be written as 1 2 3 in the cyclic permutation 1 2 3 into h. Okay, and that's the example, the first example. Then we are now going to see a different example, another example. Here we consider G equal to Z9. In this example we take G equal to Z9. That is the mother set is Z9, and it's a subset, the mother group, and its subgroup is 0 3 6. Actually it's a cyclic group also. H, see here the H, the subgroup of the given group. This group is this set is taken as the group G. This is the mother group, the group G, and the subgroup, its subgroup is H equal to 0 1 0 3 6. And this is clearly a cyclic group, the cyclic group generated by 3. as a subset of Z9. So see, we must understand, we must try to understand that it's a subgroup of Z9. Only it's a subgroup of Z9. Okay, then what are the elements of Z9? You know, the elements of Z9 are 0, 1, 2, and these are all classes actually. Classes of elements. When we consider the set of integers, from the set of integers we are making this class of integers by dividing. You know, every integer you can divide by 9. So modulo 9 is used. In addition, modulo 9 is the operation here, which is used in the which is the basis of, which makes the basis of the group Z9. Addition modulo 9. So when you want to add two elements, you have to add them as usual. You have to add the two elements. Suppose I and j are two elements in Z9. See what should we do then? Then you have to add I and j as usual. So as usual, you can add I and j, and then that sum obtained can be divided by 9 to get the remainder. So sum is I plus j, that is the sum, is divided by 9 to obtain the remainder. And that remainder will be the answer, and that will be by a quantity which is less than 9, maybe 0. So from 0 to up to 9, any quantity can be one among the quantity from 0 to 9 is the answer to that operation. Okay, that's about the group Z9. So then, with using this operation, you can this operation is very important. The same operation will be applied in defining the cosets, defining both the left and right cosets. We have to use the same operation. So let us now take an element. Here H is now chosen and H is taken, and then we one by one we choose elements of Z9. How many elements are there in Z9? Z9 contains 9 elements. See, starting from 0. 0 is the identity element in that case, because with respect to addition, here addition is the operation, and this is not the ordinary addition. This addition together with the operation of taking modulo 9, mod 9 is considered as the operation. So you know, when A is an element of is an arbitrary element of Z9. Suppose A is an arbitrary element of Z9, then A plus H is equal to, we can define A plus H equal to A plus small h, where H we want to choose an element H from H, so A plus small h, where H is an element of H. A plus small h, an element of H, and therefore in this line we can define 0. 0 is the first element here. 0 is the least element, least element in Z9. So 0 plus h we can define. 0 plus h is equal to 0 plus 0, 0, 0 plus 3, 3, 0 plus 6, 6. So that is the first coset. The first coset which is obtained. The left coset, first left coset. And then, but additionally you can see that it is equal to 3 plus h. But 0 plus h is equal to 3 plus h also. That's equal to 6 plus h also. Thus, there are 3 cosets which are same. See, when we add 3 to h, when we add 3 to h, okay, then when we add 3 to h, you know, we get the same coset, and you can add 6 to h, then also we get the same coset. And then another coset, a different coset. If you want a different coset, you have to add 1. Then when 1 is added to h, you get the elements. See, the elements in h are 0, 3 and 6. So when 1 is added, 0 plus 1, 1, and 3 plus 1, 4, and 6 plus 1, 7 are the elements which are existing in this coset 1 plus h. But you can also see that it is equal to, the same left coset is equal to 4 plus h and equal to 7 plus h. And then another, a third different left coset is obtained by adding 2 to h, 2 to h, and so we get that, when we get 2 plus h equal to 2, 5 and 8. See, 0 plus 2, 2, 3 plus 2, 5, and 6 plus 8, 8. And that equal to 5 plus h and equal to 8 plus 8. at 8 plus 8. Okay, these are the examples, very simple examples for the formation of left cosets. See, in both of these cases, we can define in the same way, in a similar way, we can define the right cosets also. We can define the right cosets. See, and that's very easy. Okay, next we are coming to the properties of cosets. So there's a set of properties, a list of properties are there that is satisfied by the cosets. So that is the next result. Let's go through that result. So let H be, so we want to state the setting where that the result is going to be applied. So for that, for giving that setting, you have to tell about the group, and also you have to say about some words about the subgroup. So let H be a subgroup of G, G be a group, and let H be a subgroup of G, and let A and B are two elements of any two elements of G. So what are the requirements for to define the properties of cosets? First we require a group G, and then we require a subgroup of a G, a subgroup that is H of G is taken here named as H, is a subgroup of G, and also we want two elements A, B, and the two elements of G which are arbitrarily chosen. Then the first property says that A is an element of AH. A is an element of AH. It is very easy because the proof is very easy because H is a subgroup, therefore H contains the identity element. When H contains the identity element, when you multiply AH, see, when you find AH, then A will be multiplied by E, the identity element, and then we get A itself. So A, the element A is that element, the product is in AH. Clearly, the A into E is in AH. Therefore, A is in AH. Next property says that AH equal to H if and only A is an element of H. See, AH equal to the left coset, AH equal to the subgroup, the chosen subgroup, if and only if A is an element of H. So, okay, suppose one thing is, how can we prove this? For that, we can come to the proof part, and suppose that AH equal to H. Suppose AH equal to H, and then A equal to AE. A equal to A into E is an element of AH equal to H. So A is an element of H. This shows that A is an element of H. We get that. So if AH equal to H, since AH equal to H, we suppose that AH equal to H, and since it happens, and consider A is equal to, A can be written as A into E, and that means A into E is an element of A into H, but AH equal to H, therefore A into E is an element of H, and since E is identity, so we get that A is an element of H. Thus we get that A is an element of H. Okay. Then conversely, suppose that the statement is that if H equal to H, we want to show that A is an element of H. If H equal to H, so initially we assume that H equal to H, then we have obtained that A is an element of H. And for the converse, we assume we have to begin with this statement. Suppose A is, assume that it is true. Suppose that A is an element of H. Conversely, if A is an element of H, if A is an element of H, then by the closure law, if A is an element of H, then by the closure law, H is a subset or equivalent set of H. See, by the closure law, A is AH into H is a subset or equivalent set of H. It's because H is a group, right? Okay. If the reason the closure law means, what does it mean by what does it mean by closure law? How do it help us? see H is a group, right? H is a group. Then and also now we know that by our assumption A is an element of H. So H is a group and A is also an element of H. A can, when A is multiplying every element of H, when we multiply any element of H, then all those elements belong to H. Therefore H is a subset or equivalent set of H. Okay. So mainly the reason behind that is that H is a group and also A is an element of H, and these are the two facts which creates that situation, which produces that required result. Okay, and so next let us assume let H be an element of H. So let us take an element of H. Let H small h be an element of H. Since A is an element of H, since A an element of H and H an element of H, and H is a subgroup. H is an element of H and also H is a subgroup. And then A inverse is an element of H. That's correct. Yeah, since A is an element of H and H is a subgroup, H acts as a group. So A inverse of A is an element of H. And this shows that A inverse into H and H is also an element of H, right? So A inverse into H is also an element of H. Thus A inverse into H is also an element of H. That's also correct. And thus H is equal to, but H is equal to E into H. You can write H equal to in the new statement. We begin a new statement. H equal to A into H, but E is equal to A into A inverse. Okay, that's correct. You can replace E by A into A inverse. A into inverse into H, and then by using associativity, applying associativity, we can write that A into A inverse H. This is equal to A into A inverse H. But A inverse H is an element of H, and A is also an element of H. That means A into A inverse H is an element of H. Okay. That then A is an element of A inverse of H is an element of H, and therefore A into A is also an element of thus H is an element of so A into A inverse H. Thus we get that this is an element of H. Okay, and A okay, A is you can think that A is an element taken from G. So A is an element taken from G. You can think about that about A only like that. So A is an element taken from G, and but A inverse H is an element of H. So A into A inverse H, and this element is an element of A into A inverse H is an element of H. Thus H is an element of AH. Therefore, whenever H is an element of H, by choosing an arbitrary element, whenever H is an element of H, we have obtained that, and that element is an element of AH. Therefore, H is a subset of AH. So this is the second statement. So here AH is a subset of H we have obtained, and now the revised inclusion is also there. H is a subset or element of AH. Combining the two, we get that AH equal to H. Next, third condition is next condition is that AB into H equal to ABH equal to ABH equal to ABH equal to A into BH, ABH, and also H into AB, HAB equal to HA into B, HA into B. Okay, how can we prove that? That's a simple proof. See, AB into H equal to, since AB into H equal to A into BH, AB into H equal to A into BH, and then AB into H, sorry, A into BH, that implies that AB into H equal to, and that implies that AB into H equal to A into BH. Similarly, B H into AB, H into AB equal to HA into B. It's HA into B, and that implies that H of AB equal to HA into B. So from this using these two, we can say that, and this is true. See, h of therefore h of AB equal to, see, h of AB equal to HA into B, and AB into H is equal to A into H, A into BH. Next, the fourth property. You have to define the how to do the fourth property. The fourth property is that AH equal to BH if and only if. You want to show that AH equal to BH if and only if A is an element of BH. AH equal to BH if and only if A is an element of BH. Okay. Coming to the proof, if AH equal to, suppose that, initially assume that AH equal to BH, then you can take A equal to A into E. A equal to A into E is an element of AH. So A is an element of AH, but AH equal to BH. So A is an element of BH. A is an element of BH. Thus we get that. Since AH equal to BH, so A is an element of BH. Conversely, if so here first one, see, AH equal to BH, thus we get that A is an element of BH. This is the thing that we want to show. So assuming that AH equal to BH, we have shown that A is an element of BH. Now to prove the conveys, you have to assume that A is an element of BH. Then we want to show that AH equal to BH. To prove that, we assume that A is an element of BH. When A is an element of BH, then you can write A equal to BH, where X is some H, or some H in H there, and then you can write A equal to BH. Okay, and then you take AH. Then AH equal to replacing A by BH. AH equal to BH into H. A equal to BH into H. But you know, H belongs to H. H is an element of H. Therefore, H equal to H itself. Thus, this is equal to B into HH. But H into H into an element in a group into the group equal to the same group. So since H is an element of H, and we take the multiplication product HH, then we get that it's equal to H. Thus we get BH. So thus AH equal to BH is obtained. Fifth property says that AH equal to BH. Either AH equal to BH or AH intersection BH equal to 5. What does it mean? Suppose some element in AH is present in BH, or vice versa. Some element in BH is present in AH, then they must be equal. All elements in AH must be present in BH, and all elements in BH must be present in AH. That means they are equal. So AH equal to BH or AH intersection BH equal to 5. To prove this, if C is an element of, let's take an element C from AH intersection BH. Suppose C an element of AH intersection BH, and then C is an element of AH and C is an element of BH. Both C is an element of both AH and BH, and then CH. Then CH equal to AH equal to BH. Why? Because C is an element of AH. When C is an element of AH, when you multiply it by, when AH is multiplied by C, then you will get AH itself. When C an element of AH, then it is AH, and similarly, since C is an element of BH, then we get it equal to BH. C into H is equal to BH. Okay, since C is an element of AH, okay, in the same way, since C is an element of BH, and then also CH then therefore, here, C is an element of AH and C is an element of BH, and also CH equal to and CH equal to AH and CH equal to BH. Thus, and therefore we get that CH equal to AH equal to BH. Okay, what's the next result? So 5. Okay, therefore AH equal to BH in that case. 1, 2. See, this is here we take that, here we assume that AH intersection BH, it is non-empty. So if we assume that AH intersection BH contains some element, then that element will be, then C is an element of AH and C is an element of BH. If it contains some common element, if AH and BH contain some common element, then then actually we want to show that then AH is then every element of AH is in BH, and also every element in BH is in AH. Then only then we get that AH equal to BH. Okay. But but then when C is an element of AH, then you can see that, you can show that CH is equal to AH. So previously we have shown that if an element, if B is an element of AH, then BH equal to AH. Okay. In the same way, we can say that if C is an element of AH, then CH equal to, and then the left coset CH will be equal to AH. So since C is an element of BH, in the same using the same argument, we get that CH equal to BH, and this shows that AH equal to BH equal to CH. Thus we get AH equal to BH and equal to CH. So in the remaining case, this is suppose the intersection is equal to empty. If the intersection is equal to empty, that is the complementary case of this situation. See the remaining case of the situation. If AH intersection BH is equal to 5, and then it is not possible. It is not possible to show this, and that means in that case AH intersection BH, if AH intersection BH is equal to 5, and then it is clearly if the intersection is equal to 5, then there is nothing to prove. So if this happens, if the intersection is not equal to 5, and then you can say that some elements are there in common to these two left cosets, and then you get that you can in that case we can prove that both left cosets are same. So in the remaining case, they are then different. They cannot be same. Remaining case is if AH intersection BH is equal to 5. If AH intersection BH is equal to 5, and then they are not equal because they do not contain. If AH intersection BH equal to 5, then they do not contain any common point. So no common point is there, and therefore they are different. Okay. Next one, the sixth statement, sixth property is that AH equal to BH if and only if if the two left cosets AH and BH are same, then A inverse of B is an element of H. Okay, if this situation is there, that if AH equal to BH, then A is present in BH and also B is present in AH, and vice versa. You can say, see, in this situation we have seen that the similar situation. So if AH equal to BH, if the two left cosets are same, then you can show that A is present, the element A is present in BH and B is present in AH. Okay, and also since A is present in BH, you can then write. See, let's go to that the proof. If AH equal to BH, see, okay, and another way also we can say that if AH equal to BH, if and only if H is equal to So by taking the inverse of B inverse, by taking the B inverse, you can or by taking the A inverse. First we take the A inverse and then we pre-multiply both sides of this expression by A inverse. Then we get A inverse into A into H is equal to A inverse into B into H. So that cancels the effect on the left side of A, and thus we get H is equal to A inverse into BH, A inverse BH. So this is there. So H is, thus we get the H is equal to A inverse BH. So then clearly it means that if A inverse B into H equal to H, then it means that A inverse B is an element of H. Okay. Therefore A inverse B is an element of H, because E is the identity element which is present in H. So A inverse B is an element of H, and that shows that if A inverse B is an element of H, we get that. And that is the thing that we want to prove. We get that A inverse B is an element of H. That's the sixth one. Okay, this is there. That we obtain that A inverse B is an element of H. And then in the seventh condition, the seventh property is modulus of cardinality of AH equal to cardinality of BH. See, that comes easily as the effect of the statement. See, here we have in the first step, in the fifth statement we have that AH equal to BH, either AH equal to BH or AH intersection BH equal to the null set. See, this is very important in proving, and that statement. AH equal to BH, either AH equal to BH or AH intersection BH is equal to 5. That means either if some of the elements of AH, one left coset is present in the other left coset, then both cosets are the same. Both cosets are same means number of elements in the first coset equal to number of elements in the second coset. So otherwise they are empty. See, if none of the elements are common, if there is no common element, then their intersection is empty. That means they are different. They are entirely different. And when they are entirely different, in that situation, when they are equal, then their numbers are, the cardinalities are same. But when there is no intersection, when they are entirely different, then what about the number of elements? See, number of elements then actually depends on the number of elements in H. Okay, but how many elements are there in H? And that is the number of elements in H into A will be with the same number. Okay, and the number of elements in BH will also be the same number. Naturally, it's because we are multiplying every element of H by B, and every element of H is multiplied by A. And also both A and B are elements of the group. Something more is required there that we want to see. It's because we have to do that. They have defined a mapping. We define a mapping, or a function is defined from H to TH. See, that's the method of a function, and then we show that this function is one-to-one and on-to. Then easily it follows that the cardinality of the two left cosets are same. So we define. So that is the one way. That's another way. I have explained. I have used the direct way of establishing that result, but this method is very accurate. This method. So let's follow this method. So for that, we define a function phi from the first left coset to the right coset left coset. Sorry, first left coset to the second left coset. Now here there is no question of right coset. So first from the first left coset to the second left coset dh, and then it is defined as phi from phi of ah is equal to bh. So that is the definition, phi of ah equal to bh. Then we will show that this definition is this function is 1, 1. How do we do that? See, suppose phi of ah1 equal to phi of ah2. Suppose phi of ah1 equal to phi of ah2. Then phi of ah1 equal to bh1 and phi of ah2 equal to bh2. Okay. Then by cancelling both sides using b inverse, we can cancel b from both sides. We get that h1 equal to h2. And therefore this implies that whenever h1 equal to h2, we get that h1 equal to h2. Okay, therefore this function is 1, 1. And then to show that it is onto, we can show that it is onto by for that we consider BH. Let's consider arbitrarily a BH, an element of a BH. We take small b into h, an element of arbitrary element of b into capital H, and then there exists AH, an element of AH, the left coset AH, element of AH, such that phi of AH equal to BH. This shows that the function is onto also. So since the function is onto and onto, number of elements in the left in both left cosets are same. Next we want to show that eighth property. This is the second last property. Eighth property says that AH equal to HA if and only if the left coset, and here we compare left and right cosets of the same element. So AH equal to HA if and only if H equal to AH A inverse. See, when we have this relation, if AH equal to HA, then by taking A inverse on both sides and multiplying it by A inverse, here we get A inverse AH, and that cancels the effect of A, and here we get A inverse into HA, A inverse HA. Or otherwise you can cross to multiply both sides by A inverse. So AH A inverse, you get AH inverse equal to H. So that's it. Therefore, if this is true, then we get that H equal to AH A inverse. So conversely, suppose that this is true. If H equal to AH A inverse, if H equal to AH A inverse, okay, then we want to establish both ways the inclusion, assuming that H equal to okay, but AH equal to HA. See, this is proved in single step actually. AH equal to HA if and only if H equal to HA if and only if H into A inverse, H A inverse equal to HA into A inverse, and that's there. If that happens if and only if H A inverse equal to H H of A if and only if H of A inverse, and that's equal to H. Therefore, if and only H A inverse equal to H. So that way we can easily prove. Otherwise we can divide it, and both way you can write the direction. You can write the proof direction. You can write the proof in both directions. Both way you can write separately the proof. Otherwise you can combine that. This is combine the proof of that if I am necessary and sufficient condition statement. So next, the last property. It states that last property states that AH is a subgroup of G if and only if. How can it tells us about the condition for AH that the product AH itself becomes a subgroup of G? When it can happen, AH is subgroup of G if and only if G A is an element of H. See, AH is a subgroup of G. The left cosset AH is a subgroup of G if and only if A is an element of H. Okay, if A is an element of H, one way we begin by assuming that AH is a subgroup. Suppose AH is a subgroup of G. If AH is a subgroup of G, then if it's a subgroup, then E is an element of AH. The identity element E an element of AH, since AH is a subgroup. Therefore, you can get that AH intersection E is an element of AH. So you get that AH intersection EH is non-empty, since E is an element of AH, E an element of AH. Therefore, AH intersection EH is non-empty. That means AH equal to, if there is one element in common to two left cosets, you know that if at least one element is common to two left cosets, the first left coset is AH, the second left coset is EH, identity element into H, then both left cosets are then same. So then AH equal to EH, AH equal to EH equal to H. That means that since AH equal to H, that means A is an element of H. So finally it reduces to A is an element of H. Then to prove that conversely, conveys part. To prove conveys part, if we assume that if A is an element of H, A is an element of H, then by using the property 2, using the property 2, then AH equal to H. So if A is an element of H, then using the property 2 by 2, then we can say that easily we can say that AH equal to H. So these are the properties of the left coset. See, also one important thing is that you can develop, you can give the same property, you can write the same property for right coset. So whatever left properties have, the left cosets have the same properties. Same properties means with the corresponding changes. So that makes that statement suitable for right coset. So with the corresponding changes, you can rewrite that rewrite on the property so as to fit for the right coset. So right coset also we can prove all these properties in a more or similar fashion. Okay, that's all. That's all here. Now, okay. Okay, and this video is now going to be closed now. Okay.